I'm going to put that in there. So yeah, if anyone just wants to type what city they're coming from. Cool.
Okay.
Nice.
Okay. All right. Yeah, it's working.
Yeah, seems like it's working. That's good.
Somebody from Sao Paulo. We have registrants from about 24 countries, so it's a very diverse audience. Yeah.
Yeah, really nice. Okay, so yeah, so thanks for doing that. It's if you want, you can use that chat function whilst the talk's going on, just so then you can ask any questions, and then we'll try and relay them during the talk. So yeah, I'm gonna hand over now to Professor Mark Hopkinson from the University of Sheffield. So off to you, Mark.
Hello, everybody. Yes, I'm Professor Mark Hopkinson from the University of Sheffield, Department of Electronic and Electrical Engineering. And so we're hosting this webinar today. I'd like to say a few words about the university and the department. So the university is one of the Russell Group members of research intensive universities in the UK. And we have a large electronic engineering department. We have around 45 staff. We host around 100 undergraduates per year and 150 master's students per year. And we have a quite strong research focus, particularly across the disciplines of electromagnetic systems, of semiconductors, and of communications. They are the three main themes of our department. So, and of course, there is a strong overlap with the subject of today's talk. We have activities within the electromagnetic group on power storage and transmission, and I think that will be of quite strong interest to those working in that area. So I'd like to thank the organizers of today, particularly Inka, for all the hard work that must go into doing this event. And particularly, I'd like to thank our speaker, Marcelo, for kindly giving us his time and hopefully to hear his enormous insight into new directions in use of AI in power transmission and storage. Sounds like a very interesting talk, and I hope you enjoy. Thank you very much.
Thank you for that, Professor Mark Hopkinson. Before the speaker begins his lecture, I would like to introduce him and give a brief background. We are privileged to have a distinguished icon in IEEE community who has made lasting contributions to advancement of electrical power systems through his research activities, journal publications, books, and teachings. On a personal note, I, as an engineer, I have read his books on modeling of power electronics and integration of renewable energy sources, and I found it to be quite useful for my learning. To start with, in this day and age, the current trajectory in the electrical power systems has now enabled the integration of communication systems and application of artificial intelligence to make power system more reliable, more controllable, and more robust. What really makes a grid to be smart is the application of communication systems. Electrical power systems are now being optimized with combination of control theory, power electronics, software-based solutions and algorithms that are developed using fuzzy logic, neural networks, machine learning, deep learning, and other tools. Any engineer that wishes to have relevance and make an impact in the emerging smart grid systems needs to understand this concept and know how to apply them. And that's why today's conversation, which focuses on these themes, couldn't have been more timely. And the University of Sheffield is proud to be hosting such an important conversation. And there's nobody else in the world who is better suited to deliver this lecture than the man who pioneered the application of artificial intelligence in power electronics, machine drives, and renewable energy, and has written many books on the subject. Our speaker is a fellow of IEEE, and he holds 2 doctorate degrees, and is a professor in electrical engineering. He has won many awards and honors, which are too numerous to mention here. And interestingly, just yesterday, he was confirmed by Colorado School of Mines as an emeritus professor. Without further ado, it's my pleasure to welcome Professor Marcelo Simoes to make his presentation. Professor, over to you, sir.
Well, thank you very much. I hope everybody hears me. And I am very honored and glad with this invitation So I'm grateful to Yanka and also to Ellie and Professor Hobson. Okay, thank you very much for this opportunity to talk to your school, and this became very diverse all over the world. As you see here, so many people saying where they are from. We have 40 attendees. It's my pleasure to talk about the subject. I have been working the past 30 years of my life, if I also include my PhD, in artificial intelligence for power electronics. On the past few years, I migrate towards power systems. So I feel that my mission today is to motivate students and to allow other researchers to be able to navigate on this integration of power electronics, power systems, into what we say is a smart grid, and we can make possible the integration of renewable energy, making our society better because we are going to make our economy more sustainable. So that's the idea of the dialogue today. I have several slides. They are formatted like a regular presentation, long, okay? I would prefer that you prepare your questions to the end so we can concentrate on the questions, okay? If it was a lecture, like I usually teach, I let the students to interrupt me. But today is better that we leave all the questions to the end. So if we can start, I can share my screen and we can start officially the lecture. Can I?
Yes, please. Thank you.
Okay, thank you. So I'm sharing my screen. And here I have, just a minute. I show from beginning here. I hope everybody sees my screen and should have my slides with the title of this page. I need to minimize this Zoom tab here, just a minute. Yeah, I think I'm ready. And there's another thing I do. I go to pointer and make this artificial laser pointer here, okay? So we behave like if we were with a laser pointer and a projector. Okay, the title of my presentation is here, the clean energy, the circular economy, and the age of artificial intelligence for smart grid systems. Each one of these subtitles could be a lecture by itself. Okay, we could talk to each one and make a whole lecture. So I try to have an approach for all of this at the same time. See if everything works. Should go to the next page. Just a minute. Okay, I think it's working now. I lost my laser pointer. Just a minute. Here. Okay, forward. I usually don't give the table of contents for talks because it's like telling the whole story of a movie, okay? So you discover as you go. Oh, if you look to the past few years, we know how important was England in the Industrial Revolution, okay? So we could define a little bit our life in the past few hundred years, that until 1785, we had a lot of animal manual labor that were replaced by machines, okay? So we had a muscle age for some time that we need muscles of people or animals to do work. Then with the Industrial Revolution, we made possible, James Watt made possible the new engines that could power machines and replace this muscle age with what we call mechanical age. Okay, so we had the invention of steam and heat engines. There was a lot of new possibilities with this industrial revolution. And in 1900 up to 20th century, we had a little more things happening. So this is just a basic understanding we could call electrical age, where there were the invention of electrical machines. Initially, we had DC machines. Some people claim that they were invented in France, which I read. Could be other places as well. And then, of course, we had Nikola Tesla inventing the AC machine, and many things happened because in addition to this steam and heat engines, we also had electrical machines. And with this, we had the need to understand how they work and how to have a model to understand. So there's a lot of things. I have a little bit more details on that in a few slides. So I could say that with the invention of the transistor, let's just skip the vacuum tubes initially. We could say that the electronics start with the vacuum tubes as well, but let's say that with the invention of the transistors, in particular for power electronics, the invention of thyristors, silicon control rectifiers, we had the birth of the power electronics. And at the same time, we could say that we had the electronics age because you start to have transistors and diodes, and those could be integrated in integrated circuits, ICs. So that made possible not only what we call power electronics today, but everything that we are so, how to say, so modern today that we have device like a phone that have a computing power bigger than any computer that was made in the 60s and the 70s. So we had integrated circuits, computers, and of course you can go towards the idea of discussing the communications, internet, and everything. So this would be a little bit of the idea and how we as electrical and electronics engineers are connected with the history of our society on the past 250 years or so, with an exponential growth in the past 80 years, 100 years. With that, technology and economic improvements, we start to use more fossil fuel. Okay, why? The energy must come from somewhere. So the first idea of the human being is to dig the earth, see what's in the soil, and bring up. So when you do that, you're going to bring, in addition to rocks and sand, coal and oil and natural gas. And that made possible a lot of growth and economic possibilities on the 20th century that were not imaginable before. However, as we do that, as we take that reserve that was there for millions of years and bring to the earth, we're going to burn, we're going to create things that were not here in our ecosystem before. So we start to have the environmental pollution, okay, all sorts of emission gases with so many problems, acid rain, global warming. Today is snowing here in Colorado. It's April 28th. It's fine. I think I should have snow, but I heard it's spring already, so something is wrong with the weather, okay? So global warming is kind of shifting seasons and so many problems that you see, and that's real. So we have an obligation to do something, and that's, I think, is the idea of my talk. You know, instead of just focusing on artificial intelligence, is what we can do as electrical engineers for a better world. How we can do it? So let's try to define a little bit the problems. we have some climate change problems. So we have to promote the energy in electrical form in a way that's sustainable, because you could have energy in electrical form where the source is still fossil fuel, okay? So we have to shift all the electrical power generation and apply advanced emission controls. We have to eliminate coal and fired power generation. Or if you cannot eliminate, we have to at least improve what we have and develop clean coal technology with carbon dioxide capture, underground sequestration. So there are many things that we can work in a, let's say, in a planning perspective, okay? There is a lot of debate, and it's not really the intention of this talk about bringing more nuclear power. So that's why I have this yellow highlight here, debatable, okay? We see that's important to preserve rainforests and the ecosystem and promote widespread reforestation. There's a lot of debate, which I do not want to bring here, particularly because this is something that I have a strong opinion against, of control of human and animal population. It's debatable, okay? But here in this dashed box, there is something we are related to. We can promote the use of renewable energy source, hydro, wind, solar, tidal, wave, geothermal, biofuels. We can replace the internal combustion engine with electric cars. We can promote mass electric transportation. We can save energy in systems that are more efficient. We can improve our generation, transmission, distribution, and utilization of electricity, and that comes the idea of smart grid. And all of this box here is only possible with power electronics, okay? So power electronics is a key technology that allows energy conversion in an efficient way, in a way that is fast if you have fast control, and flexible for further integration and communication. So power electronics is a key technology in those bullets that are important in how to solve or mitigate climate change. So if you are a power electronics person, or if you are a power systems person, and today in my age, I'm 58 years old, I learned that power electronics and power systems should be integrated and unified, because on the past 50 years, we had a track in power systems, another track in power electronics, a group of professors and researchers in this area, a group of professors and researchers in this area. What you need to do is to have a new generation of students who are motivated to understand how they merge and they are unified. So power electronics and power systems should be part of an integrated approach, okay? Eventually, we want to prevent energy waste, and we want to have energy from sustainable source. Here we have a curve that maybe you have seen before. We can digress and discuss, but we have here 1900s, and see, we go in about 2200, 2300. So what's the meaning of this? Of course, this is an image, and data will eventually be useful to make this precise, but this has been assumed to be a very reasonable way to see how is the energy depletion lifetime of several sources. You can see here that uranium is gonna finish very soon. So nuclear power is never going to be a sustainable solution, okay? There are other problems with nuclear power, and one of the problems is the reserves of uranium in the world, they are limited. Of course, you can keep digging and digging and digging and finding more ore of uranium, but still is limited, okay? So there is a limitation for uranium, and the idea is that as soon as the slope starts to be negative a little after the peak, the economists will say that the price increase will be so high that it will be not sustainable anymore. Okay. You can see that oil has some reserves for, I don't know, it's always debatable because we keep finding oil and oil is still in the Middle East or in the ocean, okay? But let's say this is 2100, could be a little further, but there is a limit for that. Gas, there is a limit, okay? Coal, we have a lot of reserves in the world. They still keep going and going, but eventually, if our society keeps on the same growth that we have and we do not have a plan to be sustainable, that means in 200 years or 300 years, we only gonna have rocks and sand on Earth, and maybe ocean and rivers, all polluted, okay? This is a discussion that we can take 30 minutes just to do the discussion. I am not asked to read this, okay? But I'll explain what's that. I'm just publishing a book by IEEE, is artificial, I never remember the name of my book. It's Artificial Intelligence for Smarter Power Systems, something like that, by IEEE. And I have a chapter that I discuss a timeline, so do not try to read, okay? I can send you this file if you want, a PDF. But here we have a timeline, see? Timeline, timeline. And on the left, I have the history of electrical engineering and electronics as a whole, and I try to emphasize things that are relevant to power electronics, power systems, electrical machines, okay? And on the right, I have the discussions on artificial intelligence, and I have here this big box showing that I have the era of cybernetics and the neural connections, and now we have deep learning, okay? So this is hard to read, but I try to put together the major events and milestones that happen since 1900, 20th century and beginning of the 21st century. And this I expanded, so the next few slides, it's an expansion of this. So this is the beginning, the top, okay? So you can see here that I started 1854 and 1819, okay? I actually was the opposite. This is the artificial intelligence things, and this is the electrical engineering. We see here George Boole published an investigation on the laws of thought, on which are founded the mathematical theories of logic and probability. So the Boolean logic that was useful for making computers 100 years after that, they were made possible 100 years before in 1854 by George Boole. So you can see about 1819 to 1822, we see here the beginning of the computers, Charles Babbage, okay, and Ada Lovelace. We know about this story, but I try to make a few things here. And then the distribution of DC by Thomas Edison and Nikola Tesla. So this is the beginning of electrical engineering. 1945 was the end of the war, and by that time, John von Neumann made the first draft report that supported a computer architecture. So we can see how electrical engineering and electronics on the right are related to artificial intelligence on the left, and I call this from 1940 to 1970s, this cybernetics age, where we had binary values to define logic, where we had binary values to define how we could model AI, artificial intelligence. Was the beginning of neural networks and the beginning of fuzzy logic. So the next slide, it would be the middle of that big figure. It's still crowded, I'm sorry, that's impossible to read, but just to relate a little bit, I say that Here we have the beginnings of neural networks, okay? And I also associated fuzzy logic. So you can see here that in 1958, we had the beginning of neural networks by Rosenblatt, who wrote a book called Perceptron, which is the main neuron of a neural network. In 1965, Professor Lotfi Zadeh published a paper giving the ideas and the foundation of what became fuzzy systems, fuzzy logic, and fuzzy reasoning. So we had neural networks going a certain path, fuzzy logic going another path. In 1970s, we still had a few developments. Neural networks had a little bit of hurt because these people here, Minsky, he wrote the limitations of the perceptron training, saying that a neural network that had more than 2 layers was impossible to train. So that was a big problem at that time. And that was only solved in 1970s when we had PhD thesis by Professor Paul Verbus, and in 1985, the backpropagation was revitalized by a group of people. Okay, I work about these ideas in my book. And here on the right, I talk about some theoretical things and some developments in electronics. I, of course, put myself here because I'm doing this, so I put my contribution that started in 1993, where I first presented a paper on fuzzy logic, okay, in a conference in Toronto, in Canada. I was in my PhD, and that was my first published paper. Here we have a few more developments. We call connectionism, this age of neural networks. And they came to a kind of halt because pretty much we had an explosion of so many topologies of neural networks. But we had a few developments on the last few years, starting around here, you see. Yeah, I have a papers here, but see 2010, so that is 11 years ago. We had the first paper that made possible deep learning, the ratified linear unit. And we had some developments that made possible deep learning. And today, a lot of people talk about deep learning as the most important thing in neural networks, but deep learning is an approach in neural networks. So I will discuss about this in a few minutes. On your right, you still have a few things that happen in electrical and electronic engineer. You see that in 2003, IEEE made possible the distributed generation standards in connection of renewable energy with the standard 1547. And at the same time, we had a few other things happening. Fuel cells and electric cars powered by fuel cells start to be developed. Honda made a car. Silicon that has been used for semiconductors start to be not replaced, but start to have another option from the wide band gap device that allow high temperature electronics to be integrated into systems. So what we have today in technology, it's something unbelievable. The exponential growth that we had in the past 30 years, which I'm happy to be alive in the past 30 years. So I could see how we came from simple bipolar junction transistors that I used to use to what we have today, a wide band gap device. And today we have a lot of communications and a lot of controls interacting. We have this technology and approach called digital twin that makes possible simulation online and in real time with a physical system. So the simulator gets information from the physical system, trying to predict faults or trying to predict maintenance and things that will help the management of that. And digital twin is something that will be incorporated into smart grids very soon. Okay. Okay, so this is a little bit of historical things, and because it's also part of my talk, what's this circular economy? People in Europe are more familiar with the circular economy, and people in the United States pretty much have no idea what's this about. It's kind of new here. Here in the United States, there is something people call the New Green Deal, which is the big deal. It's like the green, to be a green technology, green society. But Europe is going ahead in this approach from circular economy because, see, when we had the Industrial Revolution, eventually we make waste. So we could have a one-way discussion, cradle to grave. It's a manufacturing model that comes from the Industrial Revolution, that makes what? Well, eventually you're gonna have 90% of the materials that were used to make something becomes waste, and most of it toxic. So we have to dump it, we have to cover it, we have to pray for the earth to take it back. This is not gonna happen, okay? So on the past 30 years, we start to have this RRR, reduce, reuse, recycle, which is a little bit better than cradle to grave, okay? And this reduce, reuse, recycle, the idea is that waste is food. So products should be designed in a way that after their useful life, they can provide some nourishment, some biological nutrients to re-enter the environment. Or maybe they could provide technical nutrients. You can take a battery, replace the battery, disassemble the battery and use the materials. And maybe some parts of those materials would be reused in another industrial cycle. And we will not downcycle it into waste, okay? We would have more recycling. So the idea of recycling is the idea of reduce, reuse, recycle. So we want to change from that to a circular economy. A circular economy start to be discussed and taken seriously when in 2015, the United Nations made their 17 Sustainable Development Goals. And we start to have conference and books on circular economy. Europe is moving faster and towards the circular economy. So this old approach of take, make, and waste must have a 360 degrees approach. So in a circular economy, products are made to be made again. Okay, that's the basic idea. We are not just recycling, but we are remaking the products from our products. And we can have digital technology that will allow us to track those materials, see where they start, where they go. So we can see what's the ownership. We could see that a smartphone had a path that came to certain manufacturers, so everybody will be owning their cycle in this approach. And we do not want waste to just be returned to the soil and be food. We want this structural waste to be put to effective use. So the whole system will be circular and will be sustainable if it's powered by renewable energy. The circular economy promises to generate benefits for business, society, and the environment. In addition to the circular economy, we have to have a smart city. Cities are unique because they have a high concentration of people, concentration of resources, capital, data, human resources in a small geographic area. We had a lot of intense change on that area because of the Homo sapiens. So for a smart city, we reject the take, make, waste linear approach in keeping products and resource and use for as long as possible, looping their components, approaching zero waste value, inviting opportunities for new markets and products and service. And I suggest, if you are interested in this, to take a look on this book, The Path to Transformation is Circular, the Circular Economy Handbook. We need to shift to this sustainable environment and economy. Sustainability is using resources in a way that meets the needs of today's generation without sacrificing the ability of our future generations. So green is not just being environmental, it's about livability for the long term. People move to cities, coasts, and farming lands will have risks and threats from the climate change. Investments in sustainable and resilient infrastructure today will improve livability and reduce the economic and social costs of future disasters. So waste is more than a resource. So the idea of landfills should be replaced about this 360-degree approach. A zero waste economy will never be 100% free of waste, of course, but we have to explore every opportunity to turn waste into a resource. So we understand the problems, we understand the solutions and the benefits. We just need to do it. It's time for a green technology, an evolution in research, education, and industry. So renewable energy, why that matters for you, me, and your next generation? When you look to renewable energy, I have a table here. We are engineers here. I'm assuming that most of everybody here in this chat, not in this chat, in this webinar, is an engineer. So we see here the source on your left, okay? And the power relationship, how much power we have that from that particular source. This is a metric, okay? It's a magnitude, it's a degree of magnitude. But this is important, time variation. We look to the sun. It may vary in seconds or hours, and the power is about 1,000 watts per square meter. Of course, when you have 1,000 watts per square meter and you want to convert, it depends how you are converting. If you have a solar cell, and the solar cell is, if it's good, 15%, that means 1 square meter of solar cell receives 1,000 watts from the sun, but it gives out 150 watts, okay? 50% of efficiency. So we need to convert that energy into something useful. But we start from a conversion that has an efficiency. So this is the total crude power available, and then we have to convert. That's the importance of power electronics. Sunshine may be important as a diffused, so these will be hours or days. Biofuels, it's a stored energy. We can have the assumption of 10 megajoules per kilogram. We could say the time variations are near. Wind will be in hours or minutes, and the power is proportional to the instantaneous power is proportional to the cube of the velocity of the wind. Tide has a time variation of hours. Wave has a variation of weeks. Hydro of months. We may have surface geothermal, deep geothermal, okay? So, deep geothermal, we can say that there is no variation because it's from the center of the earth. The surface geothermal is only 20 meters below the surface, half a year. It takes the average temperature of the site in 1 year to be a resource of energy. So you see here that we have this time variation and we have the availability. So what matters is we want to convert that energy in a very efficient way and make it available for our society. Okay. If you look to the electric power grid, I have here some slides that define the past, the present, and the future. Okay. The traditional way we go to school, we used to go to school, that's not the traditional way I teach anymore, but I was taught on this model. Okay. You go to school and you learn about electrical power generation. You learn that you have the bulk power system with a generation station. And then we have a substation to raise the voltage, and the voltage will be high enough to have a lower current, so we don't have copper losses. And electrical power can travel for kilometers, hundreds of kilometers, or hundreds of miles, until you get to the distribution where you have a substation that it's a big transformer. You step down and you go to feeders of voltage that will be on the order of kilovolts. 12, 26, 69, depends, okay? And then you have further substations and further transformers until the user, you and me and us, will receive 120 volts or 240 volts or 230 volts, depends. Could be 60 hertz or 50 hertz. But the traditional way to teach, model, and understand the T&D power system was this unidirectional power flow. But this is not true anymore for this 21st century. So we have to change the way we teach, even in the school when we do your research, with this simple model, okay? So this is the past. And the past was simple. As a fossil fuel or hydropower plant and a substation, the high voltage transmission, another substation, and then I have a distribution for industrial. This is not commercial, this should be residential, okay? There is a typo here. And this is a commercial. And in the past, because this was so simple and unidirectional, the system operator could pretty much control with telephone. The system operator could call engineers in the substations to fine-tune what's necessary for this power transmission. This kind of unidirectional power flow was the beginning of the grid 100 years ago. And it was a reality until 1960s, depending on the place, could be 1970s. But what we have today in the present is a little more evolved. We have a transmission control center and a distribution control center using SCADA. SCADA is based on PLCs. These are industrial. My cat's meowing. He wants to come here. In this present, we can also have, of course, the integration of some renewable energy, particularly in high voltage. So we could have wind energy integrated with the transmission side or sub-transmission. We can have some solar energy. But in the present, even though we have SCADA that allows a smart generation and a smart transmission, we don't have a smart distribution because the customers are not connected to each other. The future is what we are doing today to improve the grid, okay? In the future, we're going to have more solar systems, more solar systems, more wind energy systems, electric cars, and we're going to have more data communication with all the possible players in this diagram, okay? So this is the future. The future is a more integrated smart grid. The power system electricity needs were simpler before. The grid was designed initially to deliver unidirectional electricity. However, this structure is difficult for the rising demand for our society that needs more energy and more distribution and more availability and more reliability. And in the past 15 years, we start to have what we define as a smart grid. What's a smart grid? There are several ways to define it, but I usually like to do this. It's a two-way dialogue of electricity and information. We are not only delivering electricity, but we are associating with information. And we have this two-way dialogue exchange between the customers, the utility. We need a network of communications, controls, computers, automations with these new technologies and tools. And the future grid must be efficient, more reliable, secure, and green or greener. Okay, so this is how I talk when I want to talk about the integration of power electronics and power systems. And I like to place SmartGrid as this bridge here. So in power electronics, we have competencies in circuits, electronics and controls, computer project-based analysis and simulation. In power systems, we have the competencies in power theory, electrical power circuits, machines, power quality. For computers in power systems, you usually need power flow, voltage stability analysis. If you want to merge and unify power electronics and power systems, we have these overlapping skills that make the student, the researcher, the engineer to have an understanding of steady state and transient analysis, advanced control, and artificial intelligence. So artificial intelligence is a part, is a tool that could be useful for this integration of power systems, power electronics, power quality, and renewable energy into a smart grid. This is kind of related to the power variation that we need. So if you are in the air power systems or power electronics, you may understand a few of these bullets. So this is just to illustrate. We may have some steady state simulations, and we may have some planning. Planning could be months or years. We may have some scheduling of electrical energy, economic dispatch. This will be in hours. We may need some dynamic simulation that is slow based on steady state models that would be in limits. This would be for thermal analysis or maybe for battery storage. We may want to discuss economic dispatch. This is also in hours. We may have some slow dynamic simulations in minutes for voltage stability, thermal analysis. Then, so this is kind of the realm of economics and power systems. And this would be the realm of power electronics, where we have power energy management in seconds. And then we start to need the fast dynamic simulation, milliseconds. So for transient stability, active power control, drives of electrical machines. And then we have transient control in microseconds for really controlling the devices, the transistors, and the device that will really command power electronics. So this will be the need of microseconds. So we need electrical circuits that should be possible to operate from these very fast dynamics of microseconds, 2 milliseconds, 2 seconds, minutes, hours, days, and months. So it's very difficult to integrate all of this in this time scale. We need some modeling approach. So this is a technique we can use to discuss modeling. This would be very important for a circuit that I teach in modeling of power electronics, and the needs of simulation speeds for where you want to use your systems, okay, for real-time simulation. Electromagnetic analysis will need analysis in steady state or transient, and we may require simulators that will run in milliseconds or microseconds. I want to bring my cat here. He doesn't want to come. He just wants to meow. So the transient control usually is in microseconds. That's for time domain and transient analysis. We may need some fast dynamic simulations and power energy management. Those are in milliseconds and seconds. So we have to go from time domain and transient to steady state. We may need some studies of stability. So we may need harmonics and Fourier analysis. And if you want to plan and work with economics and planning, then is the energy management and optimization, and certainly a lot of linear algebra for that. Okay. So you see here in this slide that I already talked about a little bit the history of electrical engineering and artificial intelligence. I came into circular economy, and what I discussed so far was a kind of status of smart grid and the need of real-time simulations, hardware in the loop, and the need of merging power systems and power electronics. That would be the status. So I'm starting now, okay, I'm changing gears. So I'm starting now with fuzzy logic. We have a few more items to discuss to the end of this lecture. But in the next few minutes, I will concentrate on fuzzy logic. What's fuzzy logic about? We know and we learn and we study what's a scientific method. We observe the real world. We make analysis. We make a model, and that model we hope it's useful for decision making. And then based on our understanding of the world with the use of the model, we're going to use variables that will control the real world phenomena. Okay, so your real world will go to this observation data analysis, a model that will allow the decision maker. We can have equations for that. So engineers love equations. The equations could be linear systems, you know, algebraic systems. Linear could be big, but could be linear, pretty much a matrix. Or could be something that has dynamics, so we have to use differential equations. Or we may have issues that we can make a decision with an understanding that is approximated. And typically that's what we usually do, okay? If you drive your car from your home to, I don't know, to a store to pick up a new TV that you just purchased, maybe you think I'm going to be on the road for 45 minutes and 15 minutes on the store, and I'll be back a certain time. So you have a model in your head, and that model is an approximation because you have experience with driving, and you have experience with traffic, and you have experience in that store. That store is an easy store to go in and out, or if it's a big store that you have to go to all the 4 floors until you get out. You know which store I'm talking about. So you have a model for that, and that's an approximate model. In physics, in engineering, you're going to try to have a lot of equations to define that, okay? But in our daily life, we don't use those equations. And as we start to have problems that are more complicated, the equations become more complicated. So we have complexity that rises. So Lot Fizadeh, when he discussed fuzzy logic in 1965, he made this statement: as complexity rises, precise statements lose meaning, and meaningful statements lose precision. Okay, so that was his motto for his ideas on using fuzzy logic. Okay. So real world, let's see, what's fuzziness? Oh, let's have a simple example. You're driving your car, and you know that in that road that you're driving, the maximum speed is 80 kilometers per hour. So there is a possibility that if you are above 80 kilometers per hour, you're going to have a ticket. You're going to be a speeder. Okay. Here in the United States, the police must chase you. So it's not really pleasant. to be chased by a police. So you just stop immediately because you never know what's going to happen. Okay. In some other countries, you may have radars that just measure your speed. So depends where you are, depends how you're going to get a ticket. You have this thing here in your life that's very real for everybody of us. If you go above the speed limit, you may have a ticket. Okay. However, we know that may or may not, particularly if that's measured with a manual radar, is not a machine. Okay, you have a possibility of having a ticket. So let's say that instead of sharp function like that from 0 to 1, you have a linear slope here indicating that at 80 kilometers per hour, you may have a 20% possibility of ticket. And if you are a 90 per hour, you are for sure 100% of possibility. So from 80 to 90, you may or may not get a ticket. Okay, so you may be a speeder or you may not be a speeder in accordance to this real fuzziness of this function that defines if you belong to the set of speeders. So fuzziness means that how much you belong to a set. Okay. We are aware that you either belong or not. This is Boolean logic, 0 or 1. But when you have a function that's a continuous function, could be monotonically rising, or could be monotonically rising, convex, and decreasing. So you have a function that defines how is your membership to a fuzzy set. Okay? And then we have to define some operations, like in Boolean logic. The basic operations are or union, and or intersection, and the negation, not. Okay, so there are the basic ones. And when you have degrees of membership, those are called membership functions, you can apply some mathematical equations to derive the final value of your operation. So there are many mathematical descriptions for that, maybe 20 or 30. In my case, I only use 2, okay? Min, max, or algebraic. There are several others. So you can define or and either by max and means or by algebra, okay? So this is easy to implement in a microcontroller. You know, taking the max and taking the mean is something that is available for any assembly language a long time ago. Here you have to make some calculations. See, the degree of membership minus the multiplication, and this is the multiplication. So we have to have a multiplication, which is easy to do in a DSP, digital signal processing. But if it's only a microcontroller that doesn't do multiplication, it's usually better to do max or min. So let's see, let's apply here. Suppose I have a vent, okay? You have an air condition and then you have a vent. So the air can be directed downward or upward, okay? The vent just takes the air upward, maximum 45 degrees, 0, minus 45 degrees, okay? So the degree of being downward goes from 1 to 0 like this, okay? And the degree of being upward is the opposite, okay? So you can say that downward and upward, and when it's and, you use the minimum. So it's the minimum of the combination, which is this membership function, okay? And if it's up, downward or upward is the union, so use the maximum. So it's the maximum on this side, and then is the maximum on that side, okay? So this is a way to define in a simple way how is the or and the and using the minimum and the max. You can also use the algebraic, but this is just a way. So where do you use fuzzy sets? We try to understand the world. We try to make a decision-making model, and we try to write rules. We try to write statements, okay? So we need a computer. In that computer, going to have a rule base. Here we have two rules, okay? And then I have the input variables that will be fuzzified. We go to the rule base here. I have two rules, rule number one, rule number two. And then I have to combine those rules somehow, and I have to give an output fuzzy set. And the output fuzzy set should be diffusified into a real number, because that real number will be used for a control action, okay? So that's what we do in a fuzzy logic system. So rules are important because they help us to understand models in a logic way. If A is true and A implies B, so B is true. But if there is a degree that A is true, and maybe that implication is not precise, so the fact that B is true or false depends. That's the idea of fuzzy logic. You know, it allows you a little further the understanding of real problems. So a statement or a rule could be defined in a if-then. If something, then an action, or then a control output, okay? We have ZDES implication. An implication is this statement that something is being evaluated for something else, okay? Using the proposal by Lotfi Zadeh, we use max and min of two fuzzy sets. And the Mandani implication, who was a researcher in 1970s in UK, because in UK was implemented the first fuzzy logic control of a steam engine, and it was made by Mandani, okay, 1971, I guess. I need to look into papers. Mandani used the minimum, okay? So we can have several variables as input. So let's say if speed is small and humidity is high and pressure is low, then the valve of the reactor is medium. So you write an understanding of a system, and then use fuzzy logic to express that statement. And then use some mathematical operators to do that calculation, okay? For example, I could have a motor controller taking a crane, okay? I have a crane, I'll move a container from the dock to a ship, okay? So I'll do that faster or slower, but I want to minimize the swing of that load. So we can describe that, and we can have a motor controller for that. And maybe the output of the motor controller, you have a fuzzy output like that. But I need to actuate in the motor. So one way is to calculate how that figure has a center of gravity. Okay, it's like finding the fulcrum of that figure, or where that figure balance. Okay, so you look at that figure, you calculate that point, like the fulcrum here, and then we diffusify. So here we have an example with two rules. Let's say you are driving your car, there is a car in front of you. Oh, so if the distance between two cars is medium, and the speed of car is medium, the speed of my car, then I brake medium to avoid collision with the car in the front. Now, if the distance between the two cars is small instead of medium, and the speed of car is medium, that means the same speed here, okay? However, the distance is small. So my intuition, if I understand this, says I have to brake harder than before. So instead of braking medium, I'm gonna brake hard. So I have rule number 1 with a set and fuzzy set for medium. I rule number 2 for a set and fuzzy set for hard. I evaluate distance and speed in this system. I have an output fuzzy set, and the fulcrum, the center of gravity, will give me a signal to actuate in the brake. Okay, so this is a way to understand a simple system with rules. Okay. There's another thing that I discuss in my books and in my publications, we don't have time here, but instead of having a fuzzy output, I have a linear equation. Okay, so I still have, if a certain variable is small and another variable is low or small and medium, but my output is a linear combination of the inputs. So you can see here that output number 1 is a certain coefficient B1 plus B11x1 plus B12x2. This is, we can do this with a linear regression, okay? It's a multivariable linear regression, but it's a linear regression. So this kind of fuzzy system has several names. I try to use the now because depending where it's from, people used to call Takashi Sugeno, and then they start to call Takashi Sugeno Gang. It's the same thing, okay? Sometimes Takashi Sugeno, sometimes Takashi Sugeno Gang. Some people call type 2 fuzzy inference. Some people call parametric fuzzy because you need parameters. Some people call relational based, okay? But it's a hybrid combination of fuzzy evaluation of inputs with linear equations in the output. So it has a more powerful mathematical solution than only fuzzy sets. How we do to identify the controller? Typically, if you go to a control systems course, you have the plant. The plant is unknown, so you have to have an identifier to find the Laplace transform of that plant, and then you design a controller. That's the typical way, okay? So you either know your plant because you know the math, or if you do not know your plant, you identify the math of that plant, and then you design a controller. So this is the approach of any control systems course, okay? In the fuzzy logic in artificial intelligence, we try to identify the controller instead of the plant. So I have an identifier, for example, for a human operator. You go into a cement plant. It's a place that they make cement, okay? So they put a lot of materials, and eventually you can make concrete, let's say. So from cement and sand and rocks, you can go to concrete. If you talk to the operators of the concrete making plant, they know how much rock and water and sand they have to mix for how long, and how long that mixture is useful to be used in a construction site, okay? So you can go and look to the operators, because if you try to identify the plant, where is the plant? You know the operation, okay? So it's very common that in artificial intelligence, we try to identify the human operator or the operation and try to replace with an intelligent control. And we can also replace supervisory systems. If you go to a fossil fuel plant, you may have a lot of PID controllers in the process, and then try to optimize all those PIDs. So you may have a supervisory fuzzy control system. Here I have a discussion that could become a discussion of papers and equations, but how wind rotates the mechanical shaft of an induction generator, and how I have a PWM inverter with vector control and Clark and Park transformation, and I want to generate power from the wind towards the grid. So I have this a configuration here of a PWM inverter and a rectifier that will push power into a three-phase grid. Okay. I could replace that with fuzzy logic. So the induction machine is here. I have a fuzzy controller for the speed. Okay. I can also make this way more intelligent. I'll discuss this a little bit towards the end. So I can have a fuzzy log speed control where instead of using PIs, I may use a logic that makes that system to drive towards zero error. That's the idea of driving towards zero error from your set point, your reference, to your feedback. Okay. We can use a fuzzy PI, so we have papers on that. I have this in my book, but this would be a controller. You have a speed feedback signal here, the reference. You have to make the error and the variation of error in per unit. So you divide by a certain scaling factor. And then you have fuzzy evaluation of error and variation of error. That's the table here. Here I have the error, the variation of error. So if the error is zero, that's great. That's what you want, okay? So if the error is zero and you do not have change of error, that means you are in the steady state point, see? You don't do anything, zero, okay? But as your error becomes positive or negative, and you're changing error, which is a derivative. Changing error is the error of this instant minus the error of the previous instant. That's a measure of a derivative, okay? So changing error could be understood as a derivative. So if the variation error is very big and negative or very big and positive, I have to have some control actions, okay? So your control action must be this is a variation control action must be integrated, and then you output your signal to your controller. That, in a nutshell, is what is a fuzzy PI control. Okay. So changing the gears, I'm looking to my time now. I have been talking a long time, 1 hour, 15 minutes. So I'll go a little faster, unfortunately, but this, what I'm giving in a talk today is a course. I have a book, it's a course. So pretty much what I'm explaining here to you today is a course of 16 weeks with exams and midterms and homeworks. Okay. So the field of neural networks has a history of some decades, I showed you in the beginning. But neural networks, they learn from data. Fuzzy logic, you learn from understanding the system in a heuristic way. It's a little more ad hoc. But neural networks, you look to input data and output data, and you want to fit a model. You can say, I can do that with statistics or with time series. Yes, you can. However, neural network is an approach and a topology that allows you to make that in a more, I'll not say intelligent, but in a more flexible way, okay? Neural networks, they can capture very complex, high-order functions, nonlinear interactions, as long as you have the proper training, the proper data. Neural networks are parallel, so you can have parallel processing. So you can have several operations be done by different parts in your systems. You can use parallel hardware to execute your operations instead of conventional microprocessors. And else, the N2 approach of neural networks are the feed-forward ones and the feedback ones. In my book, I describe the feed-forward neural networks and the feedback, and I put together here because they are kind of related. Feedback competitive, and associative neural networks. Okay, and you can make your neural network approach going in a certain feed-forward way or in a feedback competitive way, and we can use other techniques. For example, I can improve feed-forward neural networks using convolutional neural networks. I can improve associative and competitive neural networks into recurrent or reinforcement learning, and that gives rise to what we call deep learning. So what today people define as deep learning is a way to implement either a feed-forward neural network or a feedback competitive or an associative neural network. Okay. To be a deep learning approach, you are going to use a convolutional technique or a recurrent technique or a reinforcement learning technique. Okay. The backpropagation algorithm was found by 3 groups separate. At that time we didn't have internet as we have today, so we didn't have the communications that we have today. So, but the history tells us that Paul Verbus wrote his PhD thesis. Dave Parker also had another study of neural networks. And this group of Humerlat, Hinton, and Williams, they also found the backpropagation algorithm. So what's a backpropagation? You excite your neural network from one direction, you measure the error, and then to correct the error, you propagate back the error to minimize how each connection is responsible for that error. That's the idea. You go one way and then you go backwards, changing the errors in accordance to the guilt of each connection. Okay. We have a diagram here that we have to get the input and output data, set up the topology. We have to initialize with random weights, and we have to do an algorithm to minimize the error. Okay. So backpropagation is the key to do this, but there are several implementations of neural networks. Here we have all of those. Okay, we have to discuss this in a class. We have the regular backpropagation, but we also have other possibilities of gradient descent. What's gradient descent? If you imagine that your output, you plot your error in the output, and there is a minimum, you want to move along that surface until you reach the minimum. So that's the gradient descent methodology. The feed-forward neural networks, they could be seen here simple with 3 layers. So here I have 5 inputs and 2 outputs and a hidden layer. Okay, so we have to, each connection here has a weight. So I take that signal, I multiply by a weight, and this hidden layer will combine the signals from each input, and then you go through an output. There's a function to make that pass into the next layer in a nonlinear way. I'm going to show you the function. A feedback or competitive neural network is different because all of the neurons are connected and interacting. Okay, the previous one is like a linear approach from input to the output. The competitive is like a competition of the neurons to see which one is the winning one. So we have several topologies, we have several kinds of feedback. So it's possible to incorporate dynamics in this feedback competitive associative neural networks because we can provide internal feedback. Okay. I told you about the functions. Each node will have a function. We can call it squashing function or nonlinear function, but the best name is activation function. okay? So we have a function as simple as a Boolean operation, 0, 1 is a hard limit. We may have another Boolean operation from -1 to 1 is also a hard limit. We have a function that could be linear with a saturation. We can have a nonlinear function. This is the inverse tan. This is a sigmoid that's unipolar. This is a hyperbolic tan. This is a function that we usually use in deep learning, soft plus, and rectified linear unit. So this is the one that you typically use in the bottom ones, including this one, are the ones that we typically use in deep learning, and the top ones are the typical ones used in regular neural networks. And there's another one called softmax. It's a kind of an algorithm. Softmax is you are trying to estimate the probability density function of a certain output, okay? And I said figure 6.10 because that came from my book. I'm sorry, I kept this here. We have several topologies. I discussed this in a paper that I published in 2004 or 2005. It was a tutorial review in the industrial applicability of neural networks. Of course, from 2004 until today, we had the rise of deep learning. Okay? We have linear vector quantization neural networks. We may have Kahonen neural networks. They were invented in Finland, in Helsinki. They are very strong, very powerful. We have the counter propagation neural networks. The information flows in a certain way, but I have an associative neural network, a Kahonen layer that's competitive, that's also integrated. So it's very cool. I used that in 1996, I guess. I use a counter propagation neural network for a communication of acoustic waves in a pipeline of oil exploration in the ocean. That was a research that we made for Petrobras, a Brazilian company in Brazil, when I was working at the University of São Paulo. Probabilistic neural network has a supervised training and try to identify the probabilistic density function of your systems. The industrial applicability of artificial neural networks can be discussed as in accordance to their topology versus their learning algorithm. And we have problems that we should use a certain neural network versus another one. There are a few papers on that. I recommend, of course, my paper in 2004, but there are a few other papers that discuss about industrial applicability. The neural networks could be used for pattern recognition, associative memory optimization. This is a basic idea of the neural network topology in the application, depending if you want to do prediction, classification, or data association, or filtering. Smarter power systems, it's really the area that I'm investing in my career. Very soon I'll be moving to another school. It's not completely official, so you have to wait a little bit for this announcement to be official, but my area will be really to allow smarter power systems. Could be for artificial intelligence, could be because we have more communications, but the idea is that the power systems should be better against parameter variation, or improving efficiency, or improving classical controls, or improving when you have nonlinearities or cross-dependence of an input and output variables. Okay. And we have now another section of my talk that is actually also long, and time's coming for 1 hour and 30 minutes. So I will quickly go through this. The deep learning really started in 2007, 2008. and why that's important for smarter power system. So I have a few sequential bullets here. There is an increasing high penetration of solar and wind power in the electric grid. We have a bidirectional power. We have prosumers, consumers that are also producing power. For example, if you have your hybrid electric vehicle, you are a prosumer. We need integrated communication and advanced infrastructure. We need to have scheduling and operation of smarter power systems because we have uncertainty, random generation. We need accurate forecasting of energy demands in several layers in our energy management. We need to integrate with smart meters and cognitive meters to provide this data that could be used for deep learning. So we can go into machine learning possibilities and discuss supervised learning versus unsupervised learning. I suggest you to take a class in computer science because they are very good on this. But they usually go into the math, into proving this, proving that, and do such and such algorithm because it's computer science, okay? But we want to work into these bullets here: classification, regression, clustering, summarization, association, and sequential analysis. This is a diagram for a deep convolutional neural network for image recognition classification. You can see that you have many layers of neural networks with a lot of data, and we have a structure here that we say convolution plus rectified linear unit, pooling, flattening the data, and then eventually defining what you want. You use softmax for that. So if you provide this system with an image, can I identify that's a car, a truck, a van, a bicycle? Okay, or if it's none of those. The recurrent neural networks, they came from the previous recurrent the new age of recurrent networks. They are called LSTM. Okay, it's a long short-term memory. It's the idea of a recurrent neural network that was proposed in 1990s on asteroids, I would say. We have several gates to control how the data will flow, and we have a lot of math, and we need a computer powerful to do this. But this would be the diagram with all the loops and the controls of the gates. And then we can combine those long short-term memories, recurrent neural networks in a stack. So this is a neural network that's stacked to another one, that's stacked to another one. And this kind of technology is the one that is being useful for example, real-time translation. As I'm talking now in English, maybe a machine like this could evaluate what I'm talking and giving my translation to several languages in real time. Okay, so this would be an application of LSTM. Or a recurrent neural network, because it has a long memory associated to it. You can evaluate a book and feed the book to a neural network, and the book can identify in which parts of the book a character is connected to a certain personality trait of something else towards the last chapter, okay? So a neural network is capable not only of dynamic systems, but also very intensive and deep structural connections of knowledge. So it's very powerful. This is another deep neural network that was introduced in 2002 by my PhD student, Paulo Almeida. He has a PhD thesis. We published these papers where we integrate the CMAC with fuzzy sets and feed-forward neural networks with parametric fuzzy equations. That allows deep learning for long-term and short-term memory. Unfortunately, my student passed away last year. He was a professor in Brazil, so we did a very good work together. Maybe in the future I can come back to this. Smart grid and sustainable energy should be powered by renewable energy. We have to make possible electric cars and transportations and artificial intelligence, fuzzy logic and neural network and deep learning could be implemented in cloud, could be integrated with smartphones and portable device. These cloud environments will allow great integration of data storage with massive distributed computing power, with a lot of knowledge that's possible to learn with AI. Deep learning and AI could enable systems on the edge of fog computing. Deep learning-based smart grid allows advanced metering infrastructure, multi-objective optimization, many techniques of disaggregation of load, modeling, Internet of Things, demand response, smart grid computation. So there is a lot of possibilities for this new area of artificial intelligence and deep learning in smart grid, into smart cities, into the circular economy, into the sustainability that we want to have. I have a few applications, don't have time, so I'm going to skip. But I usually discuss like dynamics of neural networks, the inverse, the adaptive. I can discuss about wind energy systems. See, this is a family of wind curves. This was my PhD a long time ago, but I like to discuss because it's still current. We can discuss about this double PWM back-to-back converters to integrate induction generator to the grid using fuzzy logic. See, fuzzy logic. We have 3 fuzzy logic controls to optimize the aerodynamics of the energy conversion, to optimize the speed generation and the power injection into the grid. Okay. We can discuss about the fuzzy rules and rules tables and implementations. This was something that I also have done in the past, using neural networks for vector control of drives, estimating signals for vector control in motor drives. We can use neural networks for understanding dynamic systems. For example, delaying is a time delay system for model predictive control, using adaptive inverse model-based control. We can use neural networks to evaluate price of electrical companies, so they will adapt for something that would be on every hour for the past 10 days or every 15 minutes for the past 7 days. So this dynamics capture in different time frames could be resolved by long short-term memory units. Okay. Here I discuss what's a typical recurrent neural network and how it evolves into LSTM. This is something that I do in my course. So I discuss exactly how to make the regular recurrent neural network into the neuron that we use into the LSTM. Okay. And AI could be used for smarter power systems, for wind signals, turbine signals, gearboxes, measuring temperature, oil viscosity. We can also take the information from generator, temperature, shaft vibration, stator and rotor winding temperatures. We can measure the converter temperatures, cooling, fluid for cooling the system, the DC link voltage, DC link current. We can incorporate some signal processing, like using Fourier or wavelet expansion of selected signals. So we can design an AI system that will make possible that we evaluate the quality of that system. And another thing that It's here a reality, has been developed for the aerospace and aircraft industry in the past 25 years, the digital twin. Now it has been applied for smart grids, where digital twin will allow this online and real-time simulation of a physical system to monitor and make possible to evaluate if you have malfunctions or maintenance needs. Okay, this is the book. It will be published in a few weeks. Those are the Sustainable Development Goals from United Nations, 17. You see that starts from no poverty, zero hunger, good health and well-being, and then you go to a little more economics, health, and wealth. Okay, climate action, peace, justice, and strong institutions. So this is the way we integrate electronics, applied electromagnetics, microwaves, wireless neural networks, statistical signal processing, machine learning, wind turbines, hydropower, computer science, batteries, fuel cells, solar cells, materials, and semiconductors. And then we multiply all of this by power electronics, power systems, power quality, renewable energy, electrical machines and drives, energy management and optimization for EVs, for transportations, for the smart grid, for a smart city, for sustainability. We can have a program on clean energy, but eventually you have to go to Jedi. You should go for being a Jedi. You should work for justice, equity, diversity, and inclusiveness of all of us in a sustainable society. Thank you for the opportunity to talk to you, for this dialogue, for our story. And I hope this is the beginning, okay? Our successful journey. We dream, we dare, and we do.
Thank you very much, Professor Marcelo Simoes. Professor Marcus, is there anything you would like to add or say a word of thanks?
Well, I'd just like to thank Marcelo for a very interesting, stimulating talk. A lot of things very new to me, especially how this may be applied in the smart grid systems. And I'm not an expert in the use of neural network technologies, but clearly this is an extremely important area that probably reflects on a lot of different application systems. But I didn't realize myself that it was important here in this control and distribution of power. So yes, thanks very much. It's very, very, very interesting talk.
Thank you.
And if you have any question, please use the Q&A. We still have like 10 minutes. The professor is still available to answer your questions. So please use your Q&A window to type your questions, please.
Yeah, I hope you saw the chat because I was talking and I could not observe the chat.
Yeah.
But if you see that something should be addressed, just tell me what I should talk. I see I have some friends here in the audience. Very nice.
Yeah.
So in the Q&A section, Musa Zahari says, thank you so much for this interesting webinar. Are the lecture slides from your course available, and what is the name of your book? Oh, sorry, I'm muted.
Sorry, I was muted. You know, my cat went to come into my lap.
Oh.
Did you hear my cat? Okay, the name of my book is Artificial Intelligence for Smarter Power Systems. It was a slide towards the end, okay? If anybody wants, I prefer to not distribute the whole deck of slides, but I can send information about the book. I can send a timeline that I believe is very useful, okay? So if anybody is interested in specific parts, I can try to address. My book will be published by IEEE in England. So it'll be a book printed and published and distributed from England.
Also, just for anyone that's listening, if you actually do want to go and listen to this again, this video should be available on the IEEE website in a few days. So that's really good. Yeah. Okay, Dong Chen says, is there any limitation of AI application to power systems, for example, in terms of the reliability, or as time goes by, there are no limitations at all?
We always have limitations on anything, okay? Simple PI controller has limitations, okay? So yes, we always have limitations. I don't know if I'm prepared now to talk bad about what I love, but I will always be conscient and conscious enough to see that if a solution should not be AI, but should be another thing, that should be the solution, okay? I'm very mature to understand that maybe a solution in a certain approach is better than a buzzword. Just because artificial intelligence is a buzzword, or deep learning is a buzzword, it's not the one that you should do it. You know, if you have a good mathematical model, I still motivate you to study control systems and apply root locus and board diagrams and do the controller design. That's still a very good way, okay? So if you have a good mathematical model, maybe you don't need any fuzzy logic neural networks, nothing of that. Just use your mathematical model and things that we learned in the school, okay? But if you have something that maybe requires a lot of data aggregation, a lot of parallelization, a lot of flexibility with the information technology, you have to be amenable for that. And I'm sure that a root locus is not amenable for that, okay? So maybe a neural network, a fuzzy logic would be amenable for that, because we can incorporate new rules, we can incorporate new data, we can make a new training, we can take the neural network that was with one hidden layer and makes with two hidden layers, and eventually become a deep learning, because as you have more hidden layers, you have to have deep learning. Deep learning is because your backpropagation goes deep. That's why it's called deep learning. You grow deep. If you have a lot of layers, your error will be squashed. So you have to have a way that you do not lose the error control, okay? So deep learning is going deep into the layers. So if you need this kind of flexibility in the age of information, I believe the classic control is not a good solution, and maybe you go towards into artificial intelligence, okay? I'm not saying modern control, because you know what's a modern control is older than me, okay? Modern control is something from the 1950s and 1960s. I was born in 1963. So a modern control is already old. Don't call modern control as something so modern. Modern control is old. But artificial intelligence, even though it has been on the history, you can see on the timeline, from the 80s and 90s, it has been recently applied to power systems and power electronics. This is a brand new area that it's important for the students of this generation. So I do not know if I digressed. I typically do. Or if I was sufficient to answer to the question.
Yeah, so Azubuike Steve Alphonsus says, thank you for the wonderful and insightful presentation. And he was wondering if you can get a copy of the slides. I know before you said that you're not too comfortable with handing out just the slides, but
No, because the slides are my talks, and I have been using that. What I usually do when my talks get old, I publish in my website, okay? I used to have a website in the school I used to work, but I left my school on December 31st, so I don't have a website there. I have a website on WordPress, and very soon I'm going to have another website. So I plan to put talks and tutorials and stuff there. I usually try to, I also have a YouTube channel Sometimes I put my classes or talks there, okay? So very soon, this talk will be kind of public, but right now it's not public yet because I'm still doing this as my talk, invited talk. But you have access to this video, okay? I make very little money. Buy my book. My book, you have everything. My book will be available in 2 months.
Okay. So if there's no more questions, yeah, well, thank you so much, Dr. Marcelo Simoes, for coming. That's like been a really interesting conversation. It's, you know, it's really opened our eyes up to, you know, whole neural networks and stuff.
Thank you very much for this opportunity. I was very glad to talk to your school. I was very glad to contribute to this PES event and IEEE event, to your department. And also I was glad that we had a lot of participants from so many other places. And I hope this talk motivated them into sustainability, into how important is power electronics, and how we want to merge power electronics and power systems, and how artificial intelligence promises to be a good technology that you should invest. That was my intention today.
All right, thank you very much, Professor, and thank you to all the attendees who have stayed to the end. We really appreciate you. So in the absence of further questions, so we would like to bring this event to an end. So thank you very much. So the video will be made available. So we'll send you the link once we post it on IEEE website. So thank you, everybody. All right, all right, bye-bye.
Thank you, panelists, and thank you to all the attendees. Bye.
Okay, bye.